Welcome. Today we're going to talk a little bit about linear speed, angular speed, and arc length. So let's get our notes out and we'll get going. All right. Remember during the video, if you are falling behind in your note taking, to pause the video and get caught back up. And if you didn't understand something the first time, make sure you go back and listen to it again. Sometimes it takes a couple times through the video or the section to understand what's being said. All right, we are working in chapter 5.1 entitled Angles in your textbook. Our learning objective today is students will determine the arc length, linear speed, and angular speed of an object. So what I'm going to do is I'm going to look at our Explore problem today, and keep in mind you do have the Jamboard in Google Classroom to look at as well. So I'm going to go ahead and just back it up a little bit, all the way back to speed. So the first question I want to ask is, what is speed? And I want you to go beyond how fast an object moves. So think about that for a second. You can pause the video if you'd like. What does speed really mean? Now, if we think about speed, we see it all around us. We see it in the speedometer in the car. We see speed limits. People talk about how fast an object or slow an object's moving. But when it comes down to it, speed, if you think about it, is nothing more than how far an object is traveled, or in this case, a distance. So speed is a distance over a time. How far an object moved over a specific time period. And that's how we measure speed. Now, as we go through this lesson, keep in mind what speed is. It's distance over time. So don't lose that. All right, let's look at our problem. We're going to talk about a clock. So we have a standard non-digital wall clock. Okay, standard digital let's try that again. A standard non-digital wall clock has an hour's hand, that's the small hand, a minute hand, that's the middle-sized hand, and the second hand, which is the longest hand. And how it works is the second hand spins around the clock, measuring seconds. You can see the clock is numbered from 1 to 12, and each number represents 5 seconds. So when the minute or the second hand goes all the way around the clock, the minute hand will move one position forward, counting minutes. So when we start talking about minutes, each number represents 5 minutes. And lastly, we have the hour hand. It moves around once the minute hand goes all the way around, because there are 60 minutes in an hour and there's 60 positions. The hour hand will move one number forward. So each number represents an hour. Currently, if we look at the clock, we can see this clock says, since the hand is between the 10 and 11, it's between 10 and 11 o'clock. Our minute hand is just before the 7, and 7 represents 7 5 minutes or 35 minutes. And the second hand is on the 3, which is also represents 3 times 5 seconds. So this would be 10, 34, and 15 seconds. Okay, so our question number 1 is, how far does the tip of the second hand travel when moving from the 12 position to the 3 position? Now, the first thing I want to do as I go through my example is I want to understand what it's asking me to do. So I'm going to highlight keywords, and this one is how far. How far tells me I'm looking for a distance. So I'm thinking to myself, if I'm talking about the second hand, if it currently or used to be up here at 12, I'm talking about the tip, and then it goes down to the 3, I want to know that distance. Now, since the clock is circular, you can see that distance I'm talking about is a piece of the circumference. So what I'm going to use is I'm going to use my circumference formula. We've learned previously that circumference is 2 pi radius times the radius. So all I need to do is take my circumference formula, and since I only need a piece of it, and that piece appears to be about a quarter of it or a fourth of it, I'm just going to divide it by 4. And let me kind of demonstrate that over here. You can see that this piece is 1/4. So my circumference divided by 4 would be 2 pi r divided by 4. And as if I reduce 2 over 4, I get pi over 2 times r. Plugging that in to my plugging in my values. Now I need to find the radius. So this would be pi over 2, and my radius is 10.2 centimeters long. So I'm just going to plug it in there, bring the units with it, and that looks a little messy and hard to read, so I'm going to go back, and there it is. Let's put it back in now. Make sure you take your units. 10.2 times pi, number of pi is just 3.14, you know, it's a long decimal, divided in half, and you can use a calculator, and you're going to get about 16.02 centimeters approximately. So the distance the tip of the second hand travels from the 12 to the 3 is about 16.2 centimeters. All right, part B is saying the same thing, except now part B wants to go from 12 to 6. And we can see that's halfway around the circle. So we're going to use the same concept of taking a piece of the circumference. So this would be 2 pi r. And this time, because we're going halfway around the circle, I'm going to divide it in 2. So I'm going to take this circumference and divide it in 2. Let me rewrite that. So I want the circumference divided by 2. And we can see that 2 pi r divided by 2 is simply pi times the radius. So when I plug that in, pi times 10.02 centimeters, again, take your units, that's going to equal, using my calculator, and I'm plugging in, and I get 32.04 centimeters. Okay, so we've answered the question about how far. Now remember, we're talking about a piece of the circumference. So if I think about that piece of the circumference is known as arc length. And when I look at my arc length, and I'm going to rewrite those, I had pi over 4 times the radius for the first one, and that was for a quarter, so I'm going to go 1/4 of the circumference. 1/2 of the circumference we figured out to be pi r. Now if I go over and do my conversions, pi r, and I convert this into degrees, I'm going to make a connection between the circumference and the angle, the piece of the circumference. I'm going to say, okay, I'm going to multiply by 180 degrees times pi. You can see the pi's cancel out. 4 goes in there 90 times. That's 90 degrees. So going back to my circle, let me make a bigger circle. There we go. It's kind of hard to do with my pen here. We went the first time from here to here. There we go. And we can say this is a 90-degree angle. And it was also 1/4 of the circumference. Wow, it's not letting me write that small, so I'm going to have to move a little slower. I'll just abbreviate, kind of scribble that out for now. It's okay. It's 1/4 of the circumference. Okay, so I want to make a connection between, again, the angle and the piece of circumference. And I'm going to do the same thing with pi. Now I know pi, I don't have to do the conversion. I know pi is equal to 180 degrees. So again, when I do its circle, the angle I was looking for, get the color back, I was going halfway down. I wanted to know this piece. So that was 1/2 of the circumference. And notice the angle is 180 degrees, halfway around. The connection we're trying to make is the piece of the circumference, whether it be uh, 1/4, which when we put in the formula turned out to be pi over 4, which matched 90 degrees, which matched the angle. the piece of circumference we used, and we put it in the formula and simplified. We got pi, which matches the angle. So what we're seeing here, this piece of circumference, when we put it in the circumference formula, is matching, these numbers match the angle. These are in radian measure. These are in radian measure. And remember, a radian is the arc length created by an angle where that arc length has the length of the radius of the circle. So let me back that up. Let me say that a little more clearly now. All right, when you have a central angle, that's an angle with a vertex at the center, and the ends end on the edge of the circle, well, the ends, or the rays, the ends, will be the radius. When the arc length matches the radius, that's called a radian measure. So we kind of talked about that a little bit. So I don't want to over talk this. What we want to see is that using the piece of the circumference and putting it into our formula, we saw that the resulting formula, we had an angle in radian measure that matched the angle we were looking for. 1/4 was 90 degrees, 1/2 was 80. Therefore, we can say we have our arc length formula. Our arc length formula is given by, so when we talk about arc length, we're going to designate it S. So S equals arc length. It is our angle times the radius, but our angle must be in radian measure. There it is. We have our first formula, so make sure you get that down. And again, we were just trying to establish the connection. Okay, let's go to the next slide. So we have part 2 of our clock problem. It says, what is the speed at the tip of the hand in inches per minute? Okay, same clock. Now we're talking about the speed. So think back, we said that speed is distance over time. Now our speed we covered, and when we're going this direction, okay, so we're going in a circular direction, our speed is our circumference. So when we're looking for a distance, sorry, I said our speed is our circumference, our distance is our circumference. So we can say our distance equals our circumference when we're talking about a circle. So if I'm looking for the speed, I need to find a distance, and then it's over a time. So the key is to relate a distance to a time. Now, we're on a clock. Clocks measure time, so we have all kinds of distances related to time. In fact, if we look at our first problem where it went from 12 to 3, we have a distance on that. That distance or circumference was 16.02 centimeters. Our time it took to get there, now since that's a second hand, it took 15 seconds since each number is 5 seconds. So we have 16.2 centimeters divided by 15 seconds. And now we have a speed. We have 16.02 divided by 15, and that would be centimeters a second. However, we want inches. Okay, so let's go figure out our speed first. So I'm going to type it in my calculator. I know you can't see that, but I'm just going to type in what we have on the screen. It's 16.02 divided by 15, and we get approximately 1.068 centimeters every second. So I'm going to use a 1 down there. Okay, so I'm going to need a little more room. So my angular speed is pretty easy. So I'm going to section this off, and I apologize. I have a small screen to work on. I'm going to bring this down. This is 0.1068 centimeters per 1 second. So what I'm going to do is I'm going to have to learn some conversions. I'm going to have to do some conversions. Now, just like we learned to do conversions with radians degrees, we're going to do the same thing. We need inches per minute. So the first thing I'm going to look for is how many centimeters are in inches. So I'm going to have to Google that. So I'm going to go over here and Google that and say, just a quick Google and go, or Google search and go 1 centimeter equals how many inches? Okay, so 1 centimeter equals 0.39 inches. So maybe I'm going to reverse it a little bit. Instead of doing centimeters to inches, let's do inches to centimeters. And I apologize about that, because I think that's going to be a little easier. Inches to centimeters, there it is. So one more time, we know that 1 centimeter is 1 inch is 2.5 centimeters. So I Googled my conversion. So I'm going to set it up. Now I want to get rid of centimeters, so I need to write my centimeters in the denominator and my inches in the numerator. So 1 inch equals 2.54. And just like we did with conversions, we're going to multiply these two. But I'm not done yet. I also have to go from seconds to minutes. Okay, so I don't have to look that one up. I know there are 60 seconds in 1 minute. Now, because I want to get rid of seconds, I'm going to put the seconds in the numerator. I'm going to go 60 seconds over 1 minute. So I'm finding two where the units are equal, the point where they're equal, and then I'm setting up the ratio, keeping in mind things I want to cross out and get rid of. And then I'm going to multiply. So I'm going to get rid of my centimeters, so those go away, my seconds go away, and I'm left with my problem of 1.068 times 1, and obviously we don't have to multiply by 1, but I'm going to put it up there, and that's 60, and that's in inches, over 1. Again, we don't have to write the 1, but I'm going to do it just because it's there to illustrate what we're doing, times 2.54. The centimeters are gone, times another 1, and that's in minutes. Now, all I have to do is put this in my calculator, and a good calculator, again, is Desmos, so that's one I would use. So let's open up Desmos, and let's put in our function. So I have 1.068 times 60, and I'm going to divide that by 2.54, and my result will be 25 point, I'm going to round off to the nearest hundredth, so 25.23 inches per minute. And that's the speed of the second hand. It goes 25.23 inches. So again, we used speed as distance over time. We said distance is circumference. We relate it to a time, and we used the distance from 12 to 3, and it took 15 seconds. We could have used the distance from 12 to 6 and used 30 seconds, and we could have went all the way around just the full circumference and used 1 minute. All were feasible. And once we figured that out, the key was relating the distance time. We just used our calculator and got 1.068 centimeters per second, and then we did conversions. All right, our last one, and I apologize for the long video. Our last one is angular speed. Now we're looking for angular speed. We're talking about a speed, but instead of a distance, such as a normal distance measured in inches or centimeters, we're just talking about how fast an angle turns, like in degrees. I go degrees per minute or degrees per hour. I went 360 degrees in 2 seconds when I spun around on my skateboard or something like that. So we're talking about the angle. So again, just like the distance, I have to do the same thing. I have to relate not a distance this time, but an angle to a time. Now I do have an angle. I have a lot of angles. I can say all the way around. Okay, so I can say my angular speed So over here, I'm going to go angular speed. I'm just going to go AS is an angle, and the angle I'm going to use is all the way around the circle. All the way around the circle is 360 degrees. But because we want radians, I'm going to change it to 2 pi. So all the way around the circle is 2 pi, and it takes me, well, 1 minute to get there. 1 minute. There's no simplification here. This was kind of an easier one. There's no conversions. So the clock or angle goes 2 pi radians, so I'll put in radians per minute. Okay, hopefully that helps out. Make sure you look at the presentation from class as well, but if you can't make it to class, please use the video, or if you need some extra help. All right, you guys have a great day. If you have any questions, please email me or let me know in class. Thank you.